In this video, we solve problem 9.1.10-T from Essentials of Statistics, 6th edition by Mario Triola. The problem statement says, since an instant replay system for tennis was introduced at a major tournament, men challenged 1,432 referee calls, with the result that 430 of the calls were overturned. Women challenged 744 referee calls, and 230 of the calls were overturned. Use a 0.01 significance level to test the claim that men and women have equal success in challenging calls. Complete parts A through C below. First, we're asked to test the claim using a hypothesis test. It says, consider the first sample to be the sample of male tennis players who challenged referee calls, and the second sample to be the sample of female tennis players who challenged referee calls. What are the null and alternative hypotheses for the hypothesis test? Well, in order to figure that out, we have to look at the claim. It says, we're asked to test the claim that men and women have equal success in challenging calls. So it looks like the claim is that the proportion of men that are successful in challenging calls is equal to the proportion of women challenging calls. So it looks like the claim is actually equal to the null hypothesis, or equivalent to the null hypothesis. The claim and the null hypothesis are the same thing. And then if that's not true, P1 is not equal to P2. So the two proportions are not equal. This is our option. The null happens to be the claim, and the alternative is that P1 is not equal to P2. And then the next thing that we want to do if we're testing a claim about a hypothesis involving two proportions is we want to identify the test statistic. In order to do this, I'll share my paper with you. Okay, so this is our formula for the test statistic. This is on the Triola formulas and tables, so you'll never have to memorize this, but I do want you to understand what this represents. This is giving us a z-score corresponding to the value of P1 hat minus P2 hat that we have from our two samples, provided that the null hypothesis is true. So this is the assumed value of P1 minus P2 in our null hypothesis. And this is the standard deviation of that sampling distribution of P1 minus P2, or P1 hat minus P2 hat, provided that P1 is equal to P2. So this is an approximation of the standard deviation. So this is just a random variable minus the mean divided by the standard deviation, and that's giving us a number of standard deviations above the mean. But in order to use this formula, we need to compute P1 hat, P2 hat, and this pooled sample proportion P bar and its complement Q bar. Okay, so in order to do that, let's identify P1 hat and P2 hat. So we are told that our first population is the population of males. The sample has involving males challenging referee calls includes 1,432 males, and 430 of those calls were overturned. So we're going to think of those as successes. And so P1 hat is the number of successes out of that sample size. It's a proportion. And we get 215 out of 716, which is approximately equal to 0.30028 if I round out to 5 decimal places. Then we want to do the same thing for the second population. We have 744 challenges to referee calls from women. So the sample size there is 744, and 230 of those were overturned. So if we think of an overturned call as a success, then the number of successes is 230 in this sample. So the sample proportion is just x2 over n2. So that's 230 over 744. So we get 115 out of 372, but we want a decimal approximation. So I get that approximately. So if I round to 5 decimal places, I get 0.30914 approximately. So P1 hat minus P2 hat is this value minus this value. So I'll just write 215 over 716, that's P1 hat, minus P2 hat, that 115 over 372. Now we could use the decimal approximations here, but I want to be as accurate as possible, so I'm going to use those exact answers. Now, this P1 hat, or this P1 minus P2 is the assumed value of P1 minus P2 in the null hypothesis. Because remember, this is a z-score corresponding to P1 hat minus P2 hat in the distribution of P1 hat minus P2 hat. And the mean of the distribution of P1 hat minus P2 hat is actually P1 minus P2. And then we're told, or whenever we're running a hypothesis test, we're assuming that the null hypothesis is true, which means that P1 is equal to P2. And if P1 is equal to P2, P1 minus P2 is 0. So we've got this here, and we're subtracting 0 from that, which doesn't change things much. And then we want this expression in the denominator as an estimate of the standard deviation of that sampling distribution of P1 hat minus P2 hat. So N1 is a sample size for our first population, which was that 1,432. And then the second population had a sample size of 744, so that goes here. But we need P bar and Q bar, where P bar is the pooled sample proportion. So that's as if we're taking all of this data and we're making it into one larger sample. So we're saying, well, what is the proportion of calls that were overturned? Well, we'll take the overturned calls from both samples and we'll divide by the number of calls that were challenged. So we'll have 430 plus 230 over 1,432 plus 744. So that is 660 divided by 2,176. And if we want a decimal approximation of that, or even a simplified fraction, I'm using my calculator over here. I've got that as my simplified fraction. And then the decimal equivalent of that is, well, the decimal approximation of that is approximately 0.30331 out to 5 decimal places. And Q bar is the complement of that. So we get 379 over 544. So we're going to have 165 over 544 times 379 over 544, and we'll have the same numbers over here. And then we've got to do all that computation, and that's going to give us our test statistic. Now remember again, this is taking a distribution of P1 hat minus P2 hat that has a mean equal to P1 minus P2, which we're assuming to be 0. And the question is, okay, this P1 hat minus P2 hat, this value minus this value, it's going to be about negative 0.009 approximately. Is that value P1 hat minus P2 hat, which is negative in this case, significantly low given that the null hypothesis is true? In order to figure that out, we go from this distribution, which is approximately normal, to a standard normal distribution with a mean of 0. And we're saying, okay, what is the test statistic Z that corresponds to that P1 hat minus P2 hat? Now I could do all of this on my calculator and I could use those fractions to get exact answers, and that would help me to be as accurate as possible. So we could do the numerator first. Divided by the square root of that expression in the denominator. So we'll have 165 times 379 divided by 544. Actually divided by 544 squared, and that's in our numerator. And we're taking all of that and we're dividing that by this 1,432. Okay, that's our first term. And then we want to have this same expression in the numerator here divided by 744 over there. So we'll open parentheses twice. We'll have 165 times 379, close parentheses, divided by 544 times itself is 544 squared, close parentheses for the numerator, divided by 744, and then hit equals. And we get a z-score of approximately negative 0.43. So that's telling us that this p1 hat minus p2 hat is approximately 0.43 standard deviations below the mean, provided that that mean is equal to 0 over here. And the question is, well, given our value of alpha, is that test statistic significantly low? Because if that test statistic is significantly low, that means p1 hat minus p2 hat is significantly low, and that means we could reject the null hypothesis. If it's not significantly low, then that means that the null hypothesis may be true, so we would fail to reject the null hypothesis in that case. So that's one way of doing this. And you see, that took a little while just typing everything in. Now, we will need to take some time to type it in somewhere, but I find that this calculation of the test statistic is much easier if I use Excel. So I'm going to show you how to do this in Excel now. Now, I have used this spreadsheet so many times that I've just left it up here. It's got a bunch of zeros in it right now until I enter the x1 and x2 and p1 hat and p2 hat, until I enter all of the quantities that are appropriate here. Oops, I want to delete that as well. But once I enter these quantities, I have Excel automatically calculating the values I want it to calculate. I want to show you how to make one of these as well. So the first thing that we would do is we would list our sample size for both samples. So this was the sample of males, and this was the sample of females that were challenging referee calls. There were 1,432 male challengers of referee calls. 430 of those calls were overturned. And then for the females, there were 744 challenges, and only 230 of those were overturned. So P1 hat is this X1 over N1. So we just type equals and then select that cell and then divide by the other cell. And then we're going to do the same thing here. Take X2 and divide by N2. And then Q1 hat is 1 minus P1 hat. And Q2 hat is 1 minus P2 hat. Now, the way I had this set up, it was also automatically calculating these values over here. So I'm going to clear this out and show you how I got these values. In order to calculate my test statistic, remember we need that pooled sample proportion, P bar, because this is when we're calculating the test statistic, we're assuming that the null hypothesis is true, which means we're assuming that P1 and P2 are equal to each other, but we actually don't know what P1 and P2 are equal to. We're just saying that they're equal to the same value. Well, our best guess of what they're equal to is P bar, which comes from taking this sample of female challenges to calls, referee calls, and then adding the sample of male challenges to referee calls, and then just looking at challenges to referee calls in general. So we're going to have a larger sample. It's like putting these two samples together and making them one big sample. The sample size in our new sample is just N1 plus N2. And then the number of calls that were overturned is X2. Well, it's the number of calls that were overturned from men plus the number of calls that were overturned that were challenged by women. And then P bar is the number of successes in general over the sample size in general. And Q bar is 1 minus that value. Now notice that these values, P bar and Q bar, are the same as the values that I have down here. I had a P bar of approximately 0.30331, and then 1 minus that is going to be that approximately 69%, but in decimal form for Q bar. And see, that's exactly what we have here and here. Now to compute the test statistic, what I want is P1 hat minus P2 hat. And this is actually already populating. So I want to show you how to get Excel to compute that. So we'll type equals, and then we'll do P1 hat minus P2 hat. We've got that value right there. So our test statistic has that minus 0 in the numerator. And then we're going to divide by the confidence interval, or the estimated standard deviation that's associated not with a confidence interval, but with a hypothesis test. So we're going to divide by this expression right here. And that expression requires us to use P bar and Q bar. That's our pooled sample proportion, and then its complement. And then this expression right here with the N1 and the N2 as the sample sizes from the original samples in the denominator. Okay, so actually before I ask for my test statistic, I want to estimate or compute that estimated standard deviation for the hypothesis test. And again, this is the one that includes that P bar and Q bar, because we are assuming that P1 and P2 are equal to each other. And our best guess for what P1 and P2 are equal to is that P bar. So the estimated standard deviation in this case is the square root. So type equals SQRT, open parentheses, of P1 hat times Q1 hat. Oh wait, sorry, that's not it. Using the confidence interval one. P bar times Q bar divided by the sample size for the first sample, plus P bar, open parentheses, P bar times Q bar divided by the sample size for the second sample, which is that right there, close parentheses. And so now we have that. So now we're ready to compute our test statistic Z, which I got already on my paper as approximately negative 0.43. So that's equal to P1 hat minus P2 hat divided by, or that minus 0, that's the assumed value of P1 minus P2 in the null hypothesis, divided by the estimated standard deviation, which is right here. And if we round that to 2 decimal places, we get that negative 0.43. So we know we're getting the same answer either way. Now here, the Excel spreadsheet is actually doing the heavy lifting, but we did have to know enough about the math to ask Excel to do what we wanted it to do. So let's enter that Z-score over here. Great. And now it's going to want the p-value. I'll use Excel for this as well. Okay, now whenever you're computing the p-value, the first thing you need to think about is whether you have a right-tailed test or a left-tailed test or a two-tailed test. And that comes from looking at the alternative hypothesis. Since our alternative hypothesis has a not equal to sign, that means we're dealing with a two-tailed test. So the p-value is not just equal to this area in the left tail, it's double that area, because the p-value in this case is the probability that P1 hat minus P2 hat is less than or equal to the value from our sample. That was this. Or P1 minus P2 hat is equal or is greater than or equal to the same value, but positive on the other side. So this area is double this area, or this area is the same as this area. Theoretically, if I had drawn a better picture, it would look the same. So I'm actually doubling this area to the left. So it's 2 times that area. And that's the same thing as 2 times the area to the left of this test statistic Z. I've got Z test is approximately negative 0.43, and I want the area to the left of that. But I also want the probability that Z is equal to positive 0.43, or a value that's greater than that. So remember, the p-value is the probability of getting a test statistic as extreme as ours or more extreme. And if it's a two-tailed test, we don't care if it's as extreme as ours or more extreme on the left, or as extreme as ours or more extreme on the right. And that's why we've got the two tails. Now, to find this quantity, we can use Excel. We can also use table A2 because it is a z-score, but I think I'll use Excel instead. Okay, so our p-value is 2 times the area to the left of z equals negative 0.43 approximately. So we want 2 times the normal distribution, and then we open parentheses, and the x value we want is actually this z-score, our test statistic. Now for a standard normal distribution, the mean is 0, the standard deviation is 1, and yes, we want cumulative area to the left, so we're going to type true there. And we're doubling that because it's a two-tailed test. And so our p-value is approximately 0.6697. If we round to 4 decimal places, we'd probably get a similar value, but maybe a slightly different value for p if we used table A2 instead. So now let's enter our answer in MyLab Statistics. So we're asked to round to 3 decimal places. So that's 0.6697. So I would round to 0.670. Okay, it likes that. Very good. All right, and then it says, what is your conclusion based on the hypothesis test? So remember what your p-value is. It's a probability. It's a probability of getting a test statistic as extreme as ours or more extreme than ours. In this case, we don't care if we're more extreme by being farther to the left or to the right. There's a 67% chance of getting a test statistic as extreme as ours or more extreme. That means that there's a 67% chance of getting a p1 hat minus p2 hat equal to our test statistic, or excuse me, our sample statistic, or more extreme than that in either direction, 67%, if the null hypothesis is true. So that's saying, it's telling us that we are very likely to get a p1 hat minus p2 hat like ours, just due to chance, given that the null hypothesis is true. So we're saying that the p-value is greater than that significance level, which means that getting values of p1 hat minus p2 hat as extreme as ours or more extreme, it's highly probable relative to our significance level alpha equals 0.01. So we're not going to reject the null hypothesis. We're not going to accept it either. We're just going to fail to reject it. We can't prove that the null hypothesis is true, but we can say we don't have enough evidence to reject that the null hypothesis might be true. So we'll fail to reject it, and then we will say something about the original claim. Now, the original claim was that the population proportions were equal to each other. And the population proportions are equal to each other in the null hypothesis, and we're failing to reject that null. So what we're saying is we do not have sufficient evidence to warrant rejection of the claim that men and women have equal success in challenging calls. So we can't say that we have sufficient evidence to prove that men and women have equal success. We can't say that we're able to prove that, but we can say we don't have enough evidence to reject that idea. I know it's a double negative, but it has to do with the fact that we are failing to reject the null hypothesis. We can't prove that two things are equal. We can just say that there's enough evidence to suggest that they're not equal. And in this case, there was not enough evidence to suggest that they were not equal. Okay, great. And now we want to test the claim again, but this time we want to construct an appropriate confidence interval. Now, in order to find the confidence interval estimate for the difference between P1 and P2, we need to find that best point estimate of P1 minus P2. So that's going to be P1 hat minus P2 hat. And then we want to add and subtract the margin of error E. That distance from there to there is E, and that distance from there to there is E. So this is P1 hat minus P2 hat plus the error, and this is P1 hat minus P2 hat minus the error. So this is our upper limit, that goes there, and this is our lower limit, that goes there. Now, in order to find those, we need P1 hat minus P2 hat. We actually already have that in our Excel spreadsheet. The exact value of that was 215 over 716 minus 115 over 372. And that was about negative 0.009, I think, or 8 something, I think, like something like that. I think I'll wait to bring up Excel in order to compute that. And then the margin of error, remember, is z sub alpha over 2 for the right value of alpha times an estimated standard deviation, but this time we're not assuming that P1 and P2 are equal to each other. This is not a hypothesis test. This is a point, or this is an interval estimate of P1 minus P2. So in this case, rather than using P bar and Q bar, which makes sense when you're assuming that P1 and P2 are equal to each other, we're going to use the best estimates that we have of P1 and P2 and Q1 and Q2, which are P1 hat and Q2, or P1 hat and Q1 hat, and P2 hat and Q2 hat. So this is our estimated standard deviation this time. And again, the reason it looks different from the one over here is because when we're testing the hypothesis, we're assuming that P1 and P2 are equal to each other, which is what the null hypothesis says. When we're computing a confidence interval, we have no reason to assume that P1 and P2 are equal to each other. So we're going to use this instead. Now I'm going to use Excel for this calculation again. I've got P1 hat and Q1 hat, P2 hat and Q2 hat on my Excel spreadsheet. I just need to find the appropriate value of z sub alpha over 2. Now you have to be careful with this. This alpha is not necessarily your significance level. Sometimes it is, but sometimes it's not. So you have to think about whether that original hypothesis test was a two-tailed test or a one-tailed test. So we go up here and we see that the alternative hypothesis is that P1 is not equal to P2. So that means we have a two-tailed test. So that means the alpha actually is the area in two tails in this case. And alpha was 0.01. So we've got 1% of the area split into two tails. So we're going to have half of a percentage of the area, half a percentage point of area over here, and then half of that over there. So you've got 1% in two tails. That means you're going to have 99% of the area in the middle. So this is going to be a 99% confidence interval. And we want to find the z-score that separates that 0.005 area at the top from this area to the left of 0.9950. Now we could look that up in table A2 if we want. We could look for this in the body of the table and find the corresponding z-score, or we could use Excel. And I think I will use Excel this time. Okay, so our alpha value is 0.01. And to get z sub alpha over 2, I want a z-score corresponding to an area to the left of 1 minus alpha over 2 in this case. So I will use the norm.s.inv function. That's like the inverse standard normal distribution function. So what they're asking for here is a probability, and then they're going to give you a z-value, which is what we want. Now the probability you have to enter is not the area to the right, it's always the area to the left. So I will type 1 minus alpha divided by 2 in this case, because it's a two-tailed test. And that gives me my z-score. And then I also need, in order to compute the margin of error here, after I've got that z sub alpha over 2, I need to compute this estimated standard deviation for our confidence interval. So that's what I'm typing right here. So I go to this cell and I type equals, and then I want the square root of, this time, p1 hat times q1 hat divided by the sample size for that first sample plus, open parentheses, p2 hat times q2 hat, close parentheses, divided by that sample size, close parentheses for the whole thing, and you want the square root of that whole thing. That's the estimated standard deviation for a confidence interval. And again, we're using different values here because we have no reason to assume that P1 and P2 are equal when we are computing a confidence interval. So notice that the standard deviation for the hypothesis test is a little bit less than the standard deviation for the confidence interval. Okay, now we have enough to compute our margin of error. We've got our P1 hat minus P2 hat over here. So that was approximately negative 0.009 is what I was saying. I guess it's 0089 approximately to 4 decimal places. And the margin of error is z sub alpha over 2 times the estimated standard deviation for a confidence interval, which is right there. Hit return. And then these two values are automatically populating with P1 hat minus P2 hat plus the error and P1 hat minus P2 hat minus the error. So you would type equals, select this cell. For the upper limit, you want to add the margin of error. And then for the lower limit, you want to take that and you want to subtract the margin of error. Okay, so that is telling us that P1 minus P2 lies between these two values. So the lower limit is approximately negative 0.063, and the upper limit is approximately 0.045. And my margin of error, according to this, is approximately 0.054. And we've already computed our P1 hat minus P2 hat. Okay, so that is how we would do that. So we compute this, we take this plus this to get this value here, and then we take this minus this to get that value over there. So let's type that in for a 99% confidence interval. The lower limit is 0.063, and the upper limit was 0.045, and they did ask us to round to 3 decimal places. Great. Okay. Now, when we're testing the claim about two proportions in this class, so that we're assuming that P1 minus P2 is 0, so that P1 and P2 are equal to each other, that is an alternative form of our null hypothesis. Whenever we're trying to test that claim about the null hypothesis using a confidence interval, we just look at the interval and we see if 0 is in the interval. Because if 0 is in the interval, that means P1 and P2 could be equal to each other. It says, so let's select the right boxes here. It says, because the confidence interval limits include 0 in this case, because we're going from a negative value to a positive value, there does not appear to be a significant difference between the two proportions. Or in other words, P1 and P2 may be equal to each other. Okay, so if P1 and P2 may be equal to each other, that means that we are failing to reject the null hypothesis. And the null hypothesis happens to be the original claim in this case. So we're failing to reject our original claim. So we're going to say there is not sufficient evidence to warrant rejection of the claim that men and women have equal success in challenging calls.